Class picture this Friday. Why are we doing class picture? Well, because I thought, well, yes, it is fun. But because I thought genuinely that the last time I lectured for Calculus 3, fall of 2023, would be the last time I would be teaching a math class here. And then the Lord gave me this class. I'm very grateful. But this is that will be officially it. So to commemorate, it'll be roughly, I believe, I'll have given either just like very, very close to a little bit over or under 150 lectures in mathematics at Oral Roberts University. So sometimes I think I just forget that happened, and that A, that's kind of a little bit crazy, but B, it's been a remarkable opportunity to serve. So I want to celebrate that. I want to remember that with you guys as my last class. So this Friday after, we'll take a picture together on the GC steps. We'll walk up as a class. And then your third exam comes a week after this coming Wednesday. It's a very, very short chapter, very short unit, and all of the material basically adds on top of itself. So it's very easy, very straightforward. This is the hardest section of the entire unit for its length. So not necessarily for its conceptual difficulty, but I think the projection stuff is harder to understand than the QR factorization algorithm. But this will just feel harder because you have to remember more steps. That's really it. So here's the goal. The entire goal of this section can be summarized like this. I'm just trying to learn to find the QR factorization if I'm given a matrix to start with. And so what is a QR factorization? If I have some matrix A, I start with an A, and it's m by n, and its columns are linearly independent. So this immediately tells me I cannot take a QR factorization of everything, right? Because not every single matrix is going to have specifically linearly independent columns. So that's kind of the first thing. If that's possible, we can find some Q and some R. A equals QR. I know what you're probably thinking. QR codes, great, this must be how those work. Unfortunately, not. I was doing some research the other day because I figured that might be a question one of you would ask, and I wanted to have an honest answer for that. And I can honestly say that those two things are not in mind. So when they're doing QR codes and the way those don't work, that is not apparently related to this factorization. Where Q is an m by n matrix, the columns form an, here's our vocabulary word, right? Orthonormal basis. So orthonormal, and I put over here as a little reminder, I made a mistake in a lecture because I realized that the naming system, although frustrating, kind of makes a little bit of sense when I really think about it. Because orthonormal is coming from, take your orthogonal, you take an orthogonal set of vectors, meaning that they're all orthogonal to each other. And then I remembered, we call the process, like if I have some sort of a vector that isn't a unit vector, but I want to make it a unit vector, that very process is what we call normalizing. So then this orthonormal is when they smashed orthogonal and normal normalizing together. And so that's kind of how helped me remember that the orthonormal, this is basically they're orthogonal and unit vectors. Orthogonal and normalized columns. Yes.
Make sure, did you officially start the lecture?
Yes.
Ooh, okay, cool.
Sorry. So, I'll finish reading through this. So, if the Q has the columns are orthonormal, well, that just tells me, are they orthogonal to each other?
Yes.
And then, how long are each of those individual vectors?
M.
1, right? Because orthonormal means what?
Orthogonal was normalized.
Okay, and normalized means what?
Unit vectors.
And how long is a unit vector?
1.
Okay, so that means every single column vector of my Q should have length what?
1.
Good. For the column space, R is n by n, so we have a square matrix. It's upper triangular, it's invertible, and it has positive entries on its diagonal. And we'll worry about that construction later. Yes?
One question. For the orthogonal was normalized. If I get a set of vectors and they're orthogonal to each other, and then I normalize all of them, are they still going to be orthogonal to each other after I normalize them?
I'll answer your question like this. Say I have a vector like this and a vector like this. They are orthogonal to each other. Does making this one longer change
Okay.
the angle relationship between them? No. And actually, that's a very good question, because by asking that question, you illustrate the very procedure for making an orthonormal set. You get an orthogonal set, and then simply adjust everything so that it's like equal to 1. Did everyone catch what Samuel was asking about? Samuel, repeat your question for everybody.
If you get a set of orthogonal vectors, but they're not normalized, they have random lengths, and then you normalize all of them, are they still going to be orthogonal to each other?
And then what did I say?
Yes.
Why?
Because it's still the right angle.
Right, the angle, we didn't adjust any of the actual angles, we were just shrinking and adjusting the lengths of these things. So does it make sense that if you were asked to produce something that is orthonormal, your very natural first step would be, well, I need to make sure they're orthogonal, and then make sure that they're orthogonal. Once I've made sure they're orthogonal, then I need to make sure that they're all the same length. I need to make them all equal to length 1. So here's our question. How do I create an orthogonal basis? Because not every single basis is going to come to you already orthogonal. And we've seen a lot of examples of this, where, say I had a vector 0, 1, and another vector 1, 4. Is it possible for me to scale this vector by some constant to get this?
Yeah.
No, that's impossible. I mean, to get 0 and then 1, that's already kind of the first indication that this is just not going to work, okay? So these are linearly what? They're independent of each other. And since they're independent, do they span R2? Yeah. So this actually is a basis. This already here is a basis for R2. So we kind of talked a lot about that in the previous unit. Now, are they orthogonal to each other? Well, we can check that. If you are ever asked, now, if you're going to write down anything in your notes, please pen this in several times, okay? If you need to check if two vectors are orthogonal, simply compute the dot product. There is nothing more to that procedure except for computing the dot product. So all I'm going to do is I'll take 0 and 1, and I'll take the dot product with 1 and 4. And so I match the corresponding entries. My 0 gets multiplied with my 1, because they're both the first entries. And then I add my 1 times my 4. What is that?
4.
Okay. Is 4 equal to 0?
No.
No. So, are these orthogonal to each other?
No.
Do you see how that process, what just transpired? So if you were ever asked at any point to verify that vectors are orthogonal, that is quite literally all that is being asked of you. Nothing more, nothing less. Yes? Okay. So, well, we have a basis, that's great, but it's not orthogonal. Okay, so then, is there some sort of predictable formulaic method that spits out an orthogonal basis from just any basis that's not necessarily orthogonal to begin with? Okay? That's the question. And so that singular question motivates the title of this very section. That process gives us exactly what we want. So Gram-Schmidt is accomplishing and filling in this gap right here, is the fact that you can have a basis where the vectors aren't going to be orthogonal to each other, but by going through the algorithm, you will end up spitting out a basis that still spans exactly the same thing, so you don't change what you span, but now you've selected the correct vector so that they're all orthogonal to each other. Okay? How do we feel about that? Is there a context for what the Gram-Schmidt formula is even going to do?
No.
Okay, why do we have Gram-Schmidt?
Because we need to figure out if we can make any basis an orthogonal basis.
Yeah, so you got it.
Okay.
Yes. Okay. Am I good to erase the announcements and this?
No.
Okay, then I will erase this side first. Was that a question, Chloe? Okay. Sorry, my peripheral vision. I heard that. So here's the Gram-Schmidt process. You will need to know this because this is kind of like one of the bigger results of this unit. Michael, you might have shared an ancestor.
Yeah.
Okay. So if I'm given, to start, a basis, just a general old basis, and let's use x1 through xp, so I have p vectors in my basis for a non-zero subspace. A non-zero subspace W of Rn. Then we're going to define the following like this. So we say define what we're going to do is we'll start with the first vector. I'm going to start with the first vector v1, and we just kind of by default associate that with my first v1. So x1, we let that be our v1. Then what we do is I do, for the second vector, and I think I should say this real fast. If I have p vectors in my original basis, how many vectors should I anticipate I need an algorithm to generate for me if I'm going to have a basis that spans the same thing? P, yeah, so there's just going to be p of these things. So v2, what we do is we basically approximate. So I'm going to take my x2 vector, and what I'm going to subtract from it is going to be a familiar face, hopefully. Minus, well, I take that x2, and I take the dot product with the previous v vector, so v1, over v1 dot v1. And by just by parallel construction, what do you think is the vector I multiply right here?
V1.
No way. That's crazy. Huh. Okay. And then now if I needed to construct the next v3, so I start by, I take my x3, I say, okay, how do I need to modify my x3 in order to make sure everything is orthogonal, right? Well, I need to not only adjust, when I said we need to adjust for every single preceding vector v, I'm at 3 now. So how many preceding v's are there? There's 2. I need to combine v1 and v2. So not only am I going to make my x3 dance with the v1 guys, what goes out here by parallel construction?
V1.
But I also need to make them dance with the v2. 3 dot v2. What goes here by parallel construction? v2. So this is going to generalize itself, so that by the time I get to the last one in the list, so the pth one in the list, how do I start? Build this by analog. What's the first thing I need to put here?
XP.
Right, so I start with xp and I say to myself, okay, xp, how do I need to adjust this to make sure it's orthogonal with everything? Okay, what's the first thing I need to do?
Summation. Summation with the negative.
Yeah, we could view it as a summation, but that's to keep it things in parallel construction here visually. I take my
xp dot v1.
good dot v1.
v1 dot v1.
And that constant multiplies against
V1.
v1,
Oh, and then dot dot.
and then we would continue, right? So
Minus dot dot.
depending on how long this is, so then I would do the v2's next, so xp dot v2 dot v2, and then v2. Now do we see what's getting iterated? Is that we're going to continue to increment up my v1s, my v2s, my v3s, my v4s, right before I get to my vp. Exactly. So it's I stop right before I get to p, so at p minus 1. Because here, I wanted v3, so I stopped at v, the one right before 3, which is 2. And so that's why I'm stopping right before I get to p. And then vp minus 1 dot vp minus 1. But again, do you see how that construction, that general form of you have a vector dot something divided by, and then the vector that you just took the dot product with, that is taking it by itself. And then again, it appears as the vector that you then have outside that scalar ratio. So you're really not having to memorize a lot of like actual novel formula stuff. And you might have recognized that, isn't that just the projection of x3 onto v1, you know? The answer is yes. And you could think about it that way. And the textbook does have a presentation of the Gram-Schmidt in terms of the projection vector notation. Personally, I think that introduces a little middle step because now you need to be constantly aware of like a third component going on. But if that makes more sense to you than this way of thinking of the formula, I don't really care as long as it's right? So does this make sense? Does the formula make sense in the sense that it's not really a formula, it's more like a means of instructions to build as many as you need? Okay.
Scott,
Yes.
can we do it in an order besides 1 to p?
Technically, yes. The reason why I do it in this order, though, is because it makes the most sense. We want to keep track that we don't forget one of the projections. So, and especially because all of these are specifically subtracted from each other, there can be some like secret algebra mistakes where if you start adding the projections and then subtracting in the right, so then you get like flipped values. So the safest bet is to kind of just do it in order. This would be my recommendation. Okay. This, if I then collected my V1 through VP, that actually forms an orthogonal basis. So this is accomplishing precisely what we needed it to do. We took a basis that's not orthogonal, and we spit out a basis that is orthogonal. And guess what? We didn't break anything and we didn't mess anything up because that exact basis will guaranteed span the same exact subspace. So you don't have to worry about what if there's an exception to the rule, or if I do this and suddenly now I'm missing some access to my subspace before. No, that's not going to happen. It'll, by definition, it will always give you exactly it'll return to you the same subspace. So you don't have to worry about that. Cool. So now we can actually get on. The rest of this entire lecture is one problem.
Okay.
The problem's so long, we might need to split it into phases like the MCU. So here's our example. Find. It's always the innocently short-worded questions too that are just the most horrendous. Okay, so find a QR factorization of this matrix. A is equal to, it's going to be a 4 by 3, 1, 1, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1. So, designed in a way that you can look at that and just say, linearly independent columns, right? And if they're linearly independent, that tells me that I can do a QR factorization. So what I do is I want to think, here's my first step. I'll try to break this into steps as much as possible so that you guys can follow along as easily as possible, is the hope. Step 1. All I need to do is make a very simple observation. is that x1, I'm going to take all of the columns out of my matrix because this is going to be my starting basis. So what is x1? With more conviction, please.
1, 1, 1, 1.
Yeah, 1, 1, 1, 1. What is x2?
0, 1, 1, 1.
And what is x3?
0, 0, 1, 1.
Is there an x4?
No.
Good. This is precisely the x's that are kind of the input to the Gram-Schmidt process. Why am I needing Gram-Schmidt? Well, it's because in order to do QR factorization, if you look in the definition, Q requires an orthonormal columns. We can't even get to the normalizing part of that if we don't even have orthogonal columns. And I can sure as bet you that none of those are orthogonal to each other. For one reason, I mean, there's no negatives. So how am I supposed to get down back to 0 if I'm multiplying positive values together? So these are not orthogonal. We need to get an orthogonal basis. And only after we get that orthogonal basis can we scale everything to be length 1. And then that will be our Q. So that's the big picture strategy here. I'm going to repeat that again a little slower and make sure we all follow along with that. The Q in the QR factorization, by definition, our objective is to create a matrix. A matrix where every single column of this matrix have length 1, so they're all unit vectors, and all of those vectors are orthogonal to each other. Yes. Make sense? Okay. So, I start with the vectors that I've been given. Are the vectors that I'm given orthogonal? No. So can I just immediately use these to make my Q?
No.
What process did we just conveniently talk about that would take a not orthogonal basis and make it orthogonal? This one. Okay? Now, after we do this process, is it all ready to go in my Q? No. What's the one thing that we don't have necessarily? Normalizing. So we're going to find our v1 through v3 as orthogonal vectors, and then we're going to make u1 through u3 as the normalized versions of all of those vectors. And then, big picture, that is what Q is equal to. So the Q, so I'll give you a little thought bubble here. The Q that we're going for is quite literally the matrix u1, u2, u3, where each one of those is coming from the V's that we spit out that's been normalized. Okay. Have you all written down this formula?
Yep.
Yes.
Okay. Have a thumb on that page or slide an extra pencil into that page so you can flip back to it, back and forth, so I can erase. So, we just follow the recipe, yes? Gram-Schmidt, so this is now we've entered the second stage of this. I'm going to let, what's the very first vector we assign? v1 is equal to x1. So that's already done for us. And what is that? So what's that going to be?
1, 1, 1, 1.
1, 1, 1, 1. Ta-da, so easy. That's the entire step. Okay, next. Step 3. And now we actually need to kind of do a formula. So if I have my V2, what's the formula give for V2?
x2 minus x2 dot v1 over v1 dot v1 times the vector v1.
Very nice. And so this is quite literally plug and chug, no complications, no caveats, no weird stuff. So what is x2?
0,
0, 1, 1, 1.
Okay, good. 0, 1, 1, 1. 0, 1, 1, 1. Minus, so let's compute this dot product. So I'm taking a dot product of x2 and what? Okay, so here's my v1, that's what I'm taking the dot product with, and here's my x2. So the corresponding entries are going to go together. What's the first entry of x2?
0,
What's the first entry of v1?
1,
What's the second entry of x2?
1,
What's the second entry of v1?
1.
Do you see how this works?
Yeah.
Okay, so what's the rest of this dot product going to look like?
1.
1 times 1 plus 1 times 1.
They're watching you, okay?
Dun, dun, dun.
1 plus 1 plus 1.
So then what's the denominator going to be?
1 times 1.
4.
1 squared plus 1 squared
Four.
plus 1 squared plus 1 squared.
Yeah.
Right. Notice that when a vector is multiplied by itself, you can either write it out like this or just the squares of each one. I don't really care. I just do it like this so that it looks the same as all dot products. And also, it just looks like a bunch of frog eyes looking at you in the bog.
That's very scary.
Okay, so what is V1?
1, 1, 1, 1, 1.
Do you see how I technically don't need to teach you this section? Like, I'm doing it because it's necessary, but for all intents and purposes, raise your hand if you want to go to grad school. I actually don't want to go to grad school. Okay, what they're going to do in grad school is say, so awesome, congratulations, you survived undergrad, which means that we can finally assume you can just have common sense. So they'll give you a rule, but they won't hold your hand anymore with the rule. They'll simply be like, you're a trusted adult. You've learned in your undergrad how to take rules and turn them into procedures.
Figure it
That's
out.
your skill. That is what it means to have a degree, is the ability to do that. And so they wouldn't be walking you through stuff like this. But I am, because I think it's fun. And also because at some point, what I'm trying to do is model to you subconsciously a lot of things. What does a clean presentation of a solution look like? What does accurately showing your work and detail look like? A lot of subconscious things, okay? All right, so I have my 0, 1, 1, 1 minus, so let's simplify. What's the numerator?
3,
And what's the denominator?
4.
4.
And I'm still multiplying it by what?
1, 1, 1, 1.
Okay, so then we do the arithmetic. This is 0 minus 3/4 is negative 3/4. 1 minus 3/4 is 1/4. And then copy paste, because it's all the same. Yeah. Now, I was talking with Chloe the other day, and she doesn't like fractions. Guess what? I also don't like fractions, because
Really?
fractions are horrendous. And so what you can do is, when you get to this stage, you figure out you do your formula. Remember, the length of this doesn't matter right now. Strictly the direction is all we've cared about. So this vector is pointed in the right direction, and we just don't like how long it is because this is a really horrible way to do that. So we can just clear the fraction by scaling it by 4. So what we want to do is we want to strategically choose an easier vector to work with. So I'm going to strategically choose v2 is equal to minus 3, 1, 1, 1. Have I broken any rules with Gram-Schmidt? No. Because the only function of Gram-Schmidt was to give me orthogonal vectors. It didn't care how long those things were. And so the direction isn't changing any, and that's 10 million times easier to work with down the road. So why don't I just use the thing that's 10 million times easier to work with? So we'll use our v2 is equal to minus 3, 1, 1, 1. Question?
Will we can we do this in Pearson, or will we have to do different?
Pearson, oh, that's a good question. I don't know. Pearson should accept it, and if it doesn't, they're wrong. Okay? Because here's another thing too. If Pearson complains, give them what they want, but then for your own personal work, scale it, and then you can do your own computations that way, and then it'll give you the same answer. Yeah. So it's kind of like appeasing a toddler. It's like, okay, fine, you won, and then you just continue to do what you were doing anyway. Okay, so V3, and this is the last one we need, right? Because how many vectors did we start with?
3.
Only had 3. Is this question? Oh, okay, cool. So after this, we're kind of done with this. This is I'm technically called this step 4, so I'll call that step 4. Next step. Okay, well, you've seen it done, so do it. What is V3?
V3 equals x3 minus x3 times v1 over v1 times v1 times v1. All times v1 minus x3 times v2 over v2 times v2 all times v2.
And then it's a little stretch of the plug and chug imagination to see what comes next, right?
Sure.
0, 0, 1, 1. Dot product of x3 and v1. 0 times 1 plus
1 over 2 minus 1 over 2.
plus 0 plus 3. 0 times 1. And then 1 times 1, 1 times 1.
Why don't we just say 1 over 2?
I agree with you, Kyle, but some of us, it's very helpful to see the whole thing. Okay, and then the denominator.
4.
1 times 1 plus 1 times 1
Right.
plus 1 times 1 plus 1 times 1.
You can just adjust. That's the easy.
Oh, wait, it's just gonna be 2/4. Then just continuously just
Okay, and because of physical space purposes, I will just, let's quickly simplify this. What is that fraction?
2/4.
1
Which
over
is
2.
just
1
half.
Maybe you're
Yeah.
wrong.
He's like, and 1/5.
3 sevenths.
Actually, just the identity matrix. How did you just get?
I just do what you
It's 2 over 3 times 0, 1, 1, 1.
What's, somebody, the numerator for this next one? Spell out the dot product so I know that you know for sure how to make these dot products.
-3 times 0 plus 1 times 0 plus 1 times
And then the denominator with v2 dot v2.
-3 times
Three.
-3.
Plus
12,
I didn't think that far. Are you using v2? Interesting.
-3, 1, 1.
Yes?
Yeah.
All good? Have I kept everybody on the train this far? Is everyone still on the bus? Are the wheels in fact round and round? Okay, let's simplify this arithmetic. So this is 2 over, let's see, 9 plus 10, 11, 12.
1 over 6.
1 over 6.
You also
Good job.
Could you calculate that if you want to divide it by 7?
Okay, and then do your arithmetic here.
Use it. Like you want to do anything.
Let's see, 0 minus 1/2 plus 1/2. So that's just what, 0 then, yeah? And then 0, we subtract half, and then we subtract a 1/6. So that's minus 4/6, right?
Minus
2/3. 3, 4, 6.
And then 1 minus 1/2 minus this again. Wait, hold on a second. Why did I put minus?
Because it is minus.
The other ones are minus 2.
That's what the equation it is minus, that's right.
That's what the equation says.
Yeah, Scott.
It's,
Scott, you're cooking with gas.
that's how the formula is.
You're good.
I believe.
Don't give up, Scott. Don't
Wait,
doubt
1,
yourself.
6.
It
Yeah.
needs to be alternating.
Negative. No.
You okay?
There should be 9. Oh no, there should be 12.
He's questioning everything.
Still over close.
What are you talking about? Scott?
Let's go.
What's wrong, Scott?
Scott, have you found an inconsistency in math?
I'm trying to figure out what's going on.
Scott, you're gonna do what 1 plus 1
Random
is?
Monday.
You're gonna do what 1 plus 1
Let
is?
him to the black hole of numbers. It
Let's
can
see.
be fixed.
Do it. Come on. We don't need the rest of this lecture.
Or no, I'm being crazy. It's 1 minus 1/2, so positive 1/2. Yeah, 1/2 minus a sixth. Because then now you have, it flips over to 2/3, so it's 1/3. I was like,
Goose.
there's no way it's negative.
I'm dumb.
Okay, yeah, sorry.
That was some good existential dread.
Okay, again, do we like the way that those numbers panned out?
No. You can multiply by 3.
So we choose, the Calvinists would say God chose.
For God. For God.
V3 is equal to what?
0, -2, 1, 1.
Bingo. Ladies and gentlemen, that's Gram-Schmidt. Okay. So, let's take,
Potentially stupid question, yes, Q.
Good boy.
So, I'm just gonna start calling PSU for now. So, what, like, after we find the final answer, what does it mean for us to choose one of the V's? I understand it removes fractions, but we have our answer for, I mean, how are we just multiplying it by something?
well, class, do we have our answer?
No.
No! We need to do step
Alright.
5.
That's a step.
Okay, so this is kind of in your notes. Do something to designate these special progress points, okay? Because that is what we did all of this for, is to figure out our V1, V2, and V3.
Checkpoint.
And so, now what we're going to do is we're going to normalize. So, is V1 a unit vector? No, this is not a unit
No.
vector. We need to make it a unit vector. So I'm going to say, I'm going to show you precisely what you need to do whenever you're ever asked to normalize. In the event that you are required to know how to normalize a vector, this is exactly what you need to do. You do 1 divided by, and then you do the length of the vector. That should spit you out your constant. And then you take the vector itself and then scale your vector according to 1 over its length. So, I have 1 over, what's the length formula for V1 here?
Oh,
The
x
square root
squared,
of V1
x1
squared.
squared plus x2 squared plus x.
1 plus 1 plus 1.
Oh, the square root of 4, 2.
Yes?
Square root of
And then V1 is 1, 1, 1, 1. So what is my normalized version of V1?
1, 1, 1, 1.
It's just 1.
It's all 1.
Always has been.
Because it's 1 over 1.
Oh wait,
Oh,
it's
root
1
one.
half. 1 half.
It's
1
half.
Let's go down.
Oh, dude, it's 4.
It's 2.
Okay? What we do once we normalize this vector, we now call it, it evolved to its final form.
The unit vector.
The unit vector.
The unit
Okay.
vector.
So, how many vectors do we have that we need to normalize?
All of them.
Okay, so we only did 1, so what should I do next?
Do the same thing with the next
Okay,
one.
An
so
arrow that says math.
1 over V2. Yes.
0 squared plus 1 squared plus 1 squared plus.
Why 0 squared?
wait, where's 0 coming from?
Minus 3.
V2?
Minus 3, 1, 1, 1.
Oh, wrong one. You're right.
9 plus 1 plus 1 plus 1. Just 12.
So 12. Radical 12. Yes.
What's the vector I'm putting here?
Minus
-3, 1, 1, 1.
Okay, I'm going to tell you this right now for saving you time. Okay, don't worry about rationalizing stuff. Just say -3 over the square root of 12. I'll know exactly what you mean. Okay. 1 over the square root of 12. 1 over the square root of 12. 1 over the square root of 12. Okay, what is this one called? How are we going to label it?
U2.
U2.
Vector. U2. Wait, aren't you supposed to? Wait, isn't that an improper fraction?
Yes, I said don't worry about it though. Don't worry about it. There's a lot more. We're only halfway through this problem, so you're not going to have time to worry about that. What's the last one?
V3. The length of V3 times V3.
Okay, so what's the length of V3?
Square root of 6.
And then what vector goes there?
0, -2.
Okay, so 0, so 4, 5, 6, just leave it as the square root of 6. So I have 0 minus 2 over the square root of 6, 1 over the square root of 6, 1 over the square root of 6. What do I label this vector as? U3. Bingo. Let's take a step back and make sure everybody's on the train, okay? The very first thing we did
I thought it was a plane.
was we walk in. Okay, the very first thing we did was we took the columns, and those were our x1, x2, and x3. We realized those aren't orthogonal. Well, gee, we have an entire algorithm to fix that for us. So we did that entire algorithm to fix that for us. We then took those vectors and said, well, we still have another problem, Houston. They're not unit vectors, and so we normalized our 3 vectors and call them our U1, our U2, and our U3. Thumbs up if that's handwritten in your notebook.
Yes.
You've written this down, you're following, we feel good, yes?
Or forward, yeah.
Okay, because we're halfway done. We have the Q. We just need to organize it in a way that shows we know that we have Q. Okay. Recall from earlier what we were anticipating. How do I construct Q? What vectors are the columns?
U1, U2, 3.
Yeah, U1, U2, and U3. Well, gee, we didn't just spend the last, I don't know how many minutes finding exactly what U1, U2, and U3 are. What is U1?
I keep mistakenly putting a dot over the Q.
What's U2?
-2 divided by what? Square root of 12.
Negative 3.
Oh, this is Scott.
Yeah?
So the reason why we don't care if we change the length of it is because we already found the unit vector.
Yeah, we're gonna scale it anyway to the
okay.
unit vector, yeah.
That makes sense.
It all gets even now. It's kind of like when I get a haircut. They come in, see whatever mess I have to work with, and they say,
Hit the wall.
4. Bzzz, and it all goes to the same exact length. Okay? So, my mom doesn't appreciate it when I do that. She says that that's probably why I'm still single. I say, you know,
That's great.
what's U3?
Hey, you do.
0.
0.
What's a good band name? That's really good.
Yay! We have Q. Okay, so what's the name of the factorization? Okay, so did we find Q?
Yes.
Yay, we're very happy. Awesome. Are we done though?
No, we still have
So,
homework to figure out.
This is great. This is awesome. It's very demure, one might say.
Very mindful, very demure.
Okay,
Is there
now
ever
here
gonna be a
is the
shortcut for
formula to get R. And this formula, you just need to have memorized. And that's why it's only 3 symbols long. Step 7. So I'm going to put this here because if you forget this, it's just kind of tough. QTA.
What?
What?
That's so cool.
It's so nice.
I thought they were about to have to like project other 25 different vectors to find it. That was just a matrix multiplication. Okay.
Okay, yeah. So you do not have to, strike a deal with the Sphinx and answer its riddle. And then beat some grandpa blackjack. No, you just have to do QTA, alright? So what does that T mean? Review all the way from chapter 3. Alright, transpose. Okay, so what the transpose does is you take every single column, and instead of writing the column like this, you write it like a row across. So R is equal to, so I'm going to do that to this right here. What are the dimensions of my Q to begin with?
4 by 3.
A 4 by 3, yeah. So then if I switch those two numbers around, it becomes 3 by 4. So this is only 3 tall, and now 4 across. So that 1/2, 1/2, 1/2, 1/2, that first column, now it's just going to lie on top as 1/2, 1/2, 1/2, 1/2, like that. So then what's the second row going to be?
-3 divided by
-3
12,
over
square root of 12, and then 1, 1, 1, 1, 1, 1.
Yeah, 1 over the square root of 12, 1 over the square root of 12, 1 over the square root of 12. And then what's the last column, what's the last row?
0, -2 divided by 6. By square
2
root.
over root 6, 1 over root 6, 1 over root 6. And then this is times A. Well, that's an old face. We haven't seen A in a second. But what is A? 1, 1, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1. So let's see. What time is it?
Well, that's a
Okay.
yeah.
So what I'm going to do is I'm going to tell you. In the event you were ever to do a problem like this on, say, you're being evaluated, being able to get it to this form is kind of what matters. So it's like, and also really think about it. There's just a bunch of 1s and 0s. So where this is, it looks terrible to multiply out, but if you take, say, scratch paper and just give yourself some extra space to really write it out, this is not rocket science, okay? So what we'll do for the end of class is I'm going to tell you what this does simplify to. Okay. So here's what we're gonna do. Notice, is this an upper triangular matrix? Yes. Are all of the diagonal entries positive?
Yes.
Okay. So does that make my QR a factorization of A?
Yes.
Woo! Okay. For the remaining time of class, I want you all to practice verifying this arithmetic, okay? So your exit ticket is to do that. Verify the arithmetic in the remaining time of class. If you run out of time, work on it on your own time. But you need to verify this computation as a brush up. Yeah.
Example.
Oh, you did it?
Yeah, Jessica brings up a great question. The way you would want to actually represent your final answer is by, you would write A is equal to insert Q, insert R. So this is how it would look at the very end. Okay?
Scott,
Yes.
since the columns or the rows of R came from an orthogonal unit basis or orthonormal basis, does it automatically become upper triangular, or would there be a case where we're now gonna have to row reduce it once we get the R multiplication done?
You're asking a very good question. That putting R equals Q transpose A here is actually the summary of this clever little algebra stuff and observations you make that will always guarantee that this does work out. So you don't have to panic about there being some R that goes absolutely bonkers, right? If the R does go bonkers, guess what we say? You cannot do the factors. Either your Q is wrong and it's not truly an orthonormal, not all of them are orthonormal to each other, or the factorization simply doesn't exist. And then you were trying to do it with column, like if you took an A and the columns were not linearly independent from the get-go, then you did waste 30 minutes of your life trying to make the not linearly independent. Yeah, so, yes.
I got a question. If we were to find factor out the denominators, how would you write that in matrix form?
Don't. Just don't. Okay, like for example, as a means of review, if I want the entry in row 1, column 1, I'm going to take row 1, column 1.
Yeah.
1/2 plus 1/2 plus 1/2 plus 1/2.
Yeah.
That's 4 times 1/2 is 2.
Oh my gosh.
Yes? Say I want the entry in the, listen very careful to how I'm wording this in a way to let you know exactly which row and column to match up. Is 3/2. Give me the row and column of 3/2 here.
Okay, done.
Row.
You
Okay.
just need the bulk load,
So,
right?
row
It's super
1,
easy.
Second column.
column 2. What's 0 plus 1/2 plus 1/2 plus 1/2? That's 3 times 1/2, 3/2. Yes? Okay, just to make sure we know how that works. Okay. And then Dr. Harder, did you want to talk to them about when should they anticipate knowing that their project is approved by you?
So have y'all submitted your projects?
No.
Do you want a submission from every single person or one per group?
One per group's fine as long as you are very clear on the one proposal which people are in your group. So I can look at those and let you know on Friday.
Friday? Okay.
Maybe earlier.
Yeah.
And that's far less.
Okay, I'm going to stop this.